I believe I can start my report. Is that greetings, honorable judges and fellow opponents. Today I will be reporting the topic about three-sided dice and uncounting experiment. So first, let's take a look at the problem statement. So to land a coin on its side is often associated with the idea of a rare occurrence. What should be the physical and geometrical characteristics of a cylindrical dart so that it has the same probability to land on its side and one of its face? So now the team feels that the main focus on this topic should be about first to get the geometrical outlook of this dice, and second is to verify if this dice is truly a fair three-sided dice, or you can call it a coin also. So let's take a look at our table of contents first. First, we'll do some theory explanations about how do we get the proportions of this dice first. And second, we'll talk about some formulatic calculations. And third, we will be the introduction of the experiment, and the fourth will be the summary and the conclusion. Okay, so the first formula we use to get the outlook of this dice is that you imagine there's a sphere, okay, and we band a band on this sphere. So this band means the edge of this coin. So what we want to do is to make this sphere have same probability to land on each point of this sphere, and both on the A side, let's consider it as the A side left from the sphere, and B side, which is right from the sphere, and the band, which is considered as the edge of the coin. So what we want to do is to make sure that each probability of landing on this three sides of the sphere is equal. So after all these calculations, we can get that the proportions between h, which is let's call it the length of our edge of the coin, and the other length of the edge of the coin, their proportion will be 1 and 2 square root of 2. Okay, so we actually there's another way to calculate this geometric outlook of this dice. Is we do not consider it as a sphere, but simply just consider the green part as the edge of our coin. on the edge of the coin is 1 and root 3 and square root of 3. Okay. So now we'll move on to. Okay, so after the calculations, we get two proportions of the dice, right? But so now, what we should do is that to find a way and to verify which one of these two proportions of the dice is the real fair three-sided dice, or is both of them are the real one. So because we're talking about something about probabilities, right? So we believe that if we cannot have a massive amount of this flipping dice times, we cannot have an accurate enough result to our topic. So I use a gaming engine which can simulate quite similar, extremely similar to the real world. It is used by Unity. So okay. You can ignore there's a little gap in the middle because the computer cannot show too much dice at once in the simulation. So first we do the thinner dice. Okay, the proportion which is thinner. Okay. So we in the simulation environment, I throw the dice for 10,000 times, and what is interesting is that after counting each, like which side did the coin land, let's call it A side, B side, and the edges. Okay, so A side is about 300 times. B side is also, A side is about 380, around 380 times. B side is around 400 times, and for the edges, there's only about, I believe there's only about 200 times on the edges. So I believe that the chances for this proportion of the dice to land on edges is too small. Okay, so now second we go for a thicker one. And also, this is just a schematic picture that we cannot show, we failed to show the one that I simulated in a lot of times because the computer kind of collapsed, so I cannot screenshot. Okay, for this one, this time, the point that lands on the edge is too much. Okay, so I believe that both of these two proportions of the three-sided dice is not what a real three-sided dice should be look like. Okay, now for our conclusions. First, after I got like both two of this proportion of the dice, let's just say it's not a fair three-sided dice since one lands on the edge for too less time, another lands on the edge for too much time, right? So that means they are definitely not what a fair three-sided dice will look like, right? So I started to think that does a fair three-sided dice really exist? But after some considerations, I believe that a fair three-sided dice should be, the proportion of a real three-sided dice should be between the thinner proportion of our dice and a thicker proportion of the dice. It should be somewhere inside between these two, but it will be extremely hard to calculate out what does this coin actually looks like. Okay, next I want to talk about some flaws that may happen, like some mistakes that may happen in my experiment. First is that I only try out for like 10,000 times. So because we're talking about proportions, so we need a massive amount of the experiment. Then we can consider if this experiment is accurate enough or not. So maybe the reason I cannot find these two dice to be a fair three-sided dice is because I am lack of experiment. If I try more times, maybe it will become a fair three-sided dice. And second is about the environment I use to do the experiment. Because it is a computer programming environment, so even though that engine is extremely similar to same to how every thing that may happen in the real world, such as air resistance and how high the coin will bounce. But even though it is still a programming environment, so there may be some minor differences between that environment and the real world. So that may also cause the, well, let's just say, unmatch of the expectations and the final experiment results. And the third I want to talk about is, I didn't put it on the presentation, is that I want to, there's two things I want to mention. First is that the size of the coin. Because we have that proportions, right? But what if someday I got the same proportion of the coin, but the coin is super big? Will that still, well, let's just say, will that still we'll still have the same result if the coin is like massive? And second I want to talk about is what the coin is made out of. So to see if the different structure will affect the final result of the experiment, I still use the environment in the program, and I change how bouncy, how high the coin can bounce in the Unity program, but also to see if the result of the experiment will be the same. And what's interesting is that it does not affect the final result of the experiment. But no matter how high the coin bounce or how fast it flips, the final result will always be the same. The thinner proportion of the dice will have two less of landing on the edges, and the thicker one will have too much landing on the edges. So let's say I predict that the material the coin is made out of does not affect the final result of our experiment. And I believe that is all I report. Thank you.
So, ultimately, you use simulation for your experiment.
Yes.
Right? So, I want to ask, in your simulation, how many degrees of movement it is for the dice?
How many degrees of the movement it is for the dice? I think it was all default settings.
All default settings.
Yeah,
so
the default settings.
There are 3 degrees of rotational movement.
No, they are all the same.
All. I mean that there is X direction rotation and Y direction and B direction rotation.
Oh yes, there is.
And you fix the initial angular velocity of the dice.
Initial, can you define what is that?
I mean the initial spin. Did you spin your dice when you do this?
No, I did not spin them. They all fall directly straight onto the ground, and then they will start bounce and they will spin. So like to make it more fair, yeah.
Understand. So did you change the coefficient of restitution of the dice?
Can you define the?
I mean the bouncy, the bouncy.
Oh, only when I'm trying to see if the material will affect the final result of the dice.
Okay.
Then I change the.
So I want to know how many. So we need to do 2 models, right?
Yes.
2 models. So you didn't try to change the other height of your dice.
The other height.
Did you try to do experiment with other height?
You mean like when I drop the height when I drop the dice?
Yeah.
I didn't change that.
Okay. And did you? So your dice is evenly distributed in the simulation.
Yes.
Yeah. And where is the camera placement?
What?
Camera placement of the simulation.
I don't think that will matter, but the camera is default setting, so it's like looking like this. Yeah, the dice is right there.
The duration. opponent with the flow.
Honorable juries and fellow competitors, I'm Chen Nankai from Jingcheng High School, Ma Cha. And today I'll be the opponent for problem 7, 3-sided dice. So here's a reminder of the problem statement. The magnet point on this side is often associated with the idea of a rare occurrence. What should be the physical and geometrical characteristics of a cylindrical dice so that it has the same probability to land on this side and one of its faces? So the main focus should be the geometrical characteristics of the cylindrical dice. And the opponent also thinks that the dynamic motion of the dice is very important in the experiment and how to quantify the probability for the 3-sided dice. And here is the structure of solving this problem. So for the reporter, they didn't give us an observation of their experiment. And for the theoretical model, they proposed 2 different models to the structure of their cylindrical dice. And for the experimentation, they used simulation using the Unity game engine. And for the conclusion, they verified. Let's skip the conclusion. So for strong and weak points for the reporter, so the strong points, I think they have a clear introduction to a problem of explaining what is cylindrical dice and the probability, and they use a simulator to quantify the result, which I think is very important in the problem, which tells us to investigate the possibilities. And for some weak points, the opponent thinks that they must address up some physical phenomenon, such as the torque acting on the 3-sided dice, and incident angle that is that the dice drops on the plane, and have no theoretical consideration in the coefficient of restitution, the solid angle, the different height of the cylindrical dice, and they have and the different plane surface. And they give us no simulation video. They only give us the photo, and they have lack of investigation on the energy of the dice, and they have inadequate experimental verification on the boundary height, which is a boundary height, and the guessing, which they guess the same probability is between their 2 models, but they didn't verify with their simulations, and the air resistance. So these are some points I'd like to discuss in my discussion time. First, I will discuss about their photo, and more about how they set up their simulation, like the mass distribution of their dice and the drop height of the dice. And then I'll move on to the theory of the 3-sided dice and like the torque and what is their standard deviation and how many degrees of movement of the dice, and some other parameters that I would like to discuss with the opponent, like the geometry of the dice and how the solid angle, and the height of the dice. And I would also like to discuss how will the coefficient of restitution affect this problem, and how the release height will affect, and how the incident angle will affect the dice. So I would like to invite the reporter to discuss with me. So can you turn to the page of your photo, the simulation photo? Okay, so I remember that in your report that you said you count the dice. So is it very accurate because I see the dice?
Oh, I didn't count it like I do count it like this.
Yeah.
I set up the A set of the dice. Let's just say A, B, C. Okay.
Yeah.
So I counted. So level C, the program will automatically check for me which A, B, C side, which side of it is touching the surface.
Okay. So did you change different dropping height? Is that possible in your simulation?
Yes, we can change different heights.
Also, did you observe that when it is like the lower height, it will sometimes will not rebound and just stick onto the height? Will just stick onto one
You mean the point doesn't bounce?
Yeah, it doesn't bounce.
Well,
Did you observe the boundary height?
So that will cause the dice will just, all of the dice will just fall on the edges.
So did you verify with your simulation that what is
I try to set the tuning of bounciness to 0.
Okay.
And because my default is that the dice will drop straight, right?
Yeah.
So it's called the C side, which is the ages.
Yeah.
It will be like all of the dice will be back on.
Okay, so did you get the boundary height of the
Boundary
dice?
height.
Yeah, boundary height, like it will not bounce, and you will not observe the same probability, the probability distribution.
Can you repeat your question?
What I mean is, did you find the boundary height? Like because you got the cylindrical dice and you just land over here. So did you find the height? But it needs to be higher to observe this phenomenon. Like over a certain amount of height.
Well, because I didn't do when the bounciness is set to 0.
Okay,
right?
so the opponent doesn't think that it needs to be like 0 bouncy to find the boundary height. Okay, but because sometimes that when it is too low, so it has the low energy, so that it would just land on
The
like
edges.
the here or the edges.
Yes.
So can you agree with me?
Yes.
So in order to find the probability distribution, it needs to be over a height, over a certain boundary height. Okay, so and I also want to ask about what is the material of the dice.
The material, I believe it's set to the default with wood.
Oh, it is a wood dice.
Yeah, wood.
So
I also try
so it is also like a rigid body dice.
rigid body.
Yeah, it will not deform.
Form.
Yeah.
Oh, you mean like it
Yeah,
will
you will
like change the
yeah, I will change.
geometric characteristics of it, right? Yes, it will.
Okay, so you proposed two model, and did you try to do like other different? So you only do two model, am I correct? Am I correct?
In a simulation, yes. And I also dropped like a normal
Okay.
in the real world.
So I want to discuss like some of the dynamic motion of the dice because the opponent think that is very important. So when it is above a certain height, that the dice, the bouncing and the motion and the rotating is too complex. So the opponent think that it has to be like it has to be lower a certain height. So the bouncing is not that random. So the opponent think there is a random height because the rotating of here is too random. Can you agree with me?
Well, if you like, let's say if you drop the dice from a really high place, right? And if I did try to not let the dice drop, just like you just let it go, right? In a simulation, it will kind of flip during falling, right? So you're saying that I should consider it as a variable when does it to see if it affects finance.
Yeah.
So I believe when I dropped it from like extremely high distance from the surface, that this flip will be too random and it cannot be considered as a variable.
Yeah, I agree with the reporter. So what do you think that is the final that caused the cylindrical dice to land on its edges or on its tail?
Again,
What do you think that it makes the cylindrical dice to land on the edge or the tail?
what makes it to
Yeah. So the only thing that it is the torque that causes. So the final torque of acting on the cylindrical dice will affect the probability that causes the dice. So the incident angle will affect the dice, and also because it is the torque that causes the final to reach whether it lands
which
on
size do you think on it?
yeah, so the opponent also think that the geometry of the dice is correlated to the torque. Can you agree with me? And the incident angle and the geometry will affect it.
Or yes, I agree.
Okay, so the dynamic motion, I'm talking about the random phase over here. I think that it has to be neglected. So what I'm trying to say is you have to be to be under a certain height to have to observe this because because when it is too high, it would always bounce over here, and it would like have
random flipping and angles to make before it lands on her.
Yeah, so I also want to talk about some problems. Okay, so how do you think that the restitution of coefficient would affect the bounce affect the bounce?
I'm going to explain the restitution.
So the bounciness of the dice, how would it affect?
Well, it's like kind of like different materials, right?
Yeah.
Because different materials will have the different bounce. What the word you said is called
Coefficient of restitution.
Coefficient of restitution. I believe when I tried enough lot of amount of the dice, it will how bouncy the dice will not affect the final result. That is not from theory. That's from the experience.
So
no matter how high the dice will bounce, and no matter how high you drop it,
so
if you have enough amount of experiment data, the data will always be.
Okay, so the reporter agrees with me that the coefficient of restitution and geometry will affect the possibility of the three-sided dice.
Yes.
Yeah. Okay, so can you show data that what is your like the exact count of your 10,000?
I have to apologize because I cannot. It is showed up to the computer, right?
Yeah.
But because this is simulation and I'm trying too much time, so the computer cannot be screenshotted.
Also, okay, I understand. So you didn't find what is your standard deviation of your data, right? So standard deviation.
Yeah.
Okay, so you didn't find a standard deviation, and okay, so and you didn't do like just because you do computer simulation, so it is quite complex to me that you didn't try like other kinds of dice. So
what do you mean?
Yeah,
other kind of dice?
So do you think that shorter dice will have or a higher dice would be more suitable?
Yeah, the proportion of the dice have to be based on these two models. So you mean like bigger dice with the same proportion? Is that what you mean?
Yeah.
Well, there's I tried it in the limit to make the dice as big as it can. It does not affect the final result of the.
Okay, so in your bouncing, it is like it has it has a 6 degree of movement of your dice, so it can rotate like x, y, z plane, and it can bounce like x, y, z. So did you try to like just do it on the x, y plane?
No, this is a 3D simulation.
Okay, so and do you try to you didn't quantify the possibility of your model?
Quantify the possibility.
Yeah.
So which means
the result of the data.
I do have the result of the data.
Okay. Can you show it?
It's like because you tried that the computer will kind of collapse.
Okay.
You understand?
So
you cannot be screenshotted.
Okay.
So yeah.
I would like to end my discussion line. So my discussion, firstly, I asked about the reporter that their initial simulation setup, and I tried to discuss with him that how the torque is important on the possibility that the dice on the falling of the dice, and how is geometric and the coefficient of restitution will affect the possibility. And I also discussed some about the experimental data, but they said that due to their computer that they didn't show us the data, so I cannot see what the standard deviation of the data, which I think that is a difficulty. And so this is the end of my discussion. Thank you.
Reviewer proposed question.
First of all, my question for the reporter is, do you believe your simulation is accurate?
Yes.
Do you have the physical equation for your simulation, the physics used in your engine?
The physics used in my.
Did you program that engine?
I didn't. It was like a default settings from.
Then how did you ensure that this engine is accurate?
Because you can see the engine yourself. It is very like almost the same as the field.
Did you have a graph or any form of data?
As I mentioned, when I tried to log a massive amount of the experiment, the computer will get it.
Do you believe your simulation is accurate?
I believe, but since they use wood as their material, so
I'm talking about the simulation.
Okay,
Do you believe the physics of the simulation is accurate?
Yeah, I believe.
Even though the physics doesn't include air resistance and many other factors?
Excuse me, I want to clarify that it do includes air resistance as one of a function inside of the program.
Okay. Do you believe that this the system of dropping the dice is a chaotic system?
A chaotic system, that means like a chaos system.
Yeah.
I do think, yeah.
Do you believe
It is. It is. Well, but only when the height that you drop the dice is tall.
Okay. So when you say this is a chaotic system, then do you believe that spinning affects, if you spin the dice when you drop it, does it affect what result you get?
Yeah, it affects because the incident angle that causes the torque, and also the spinning causes air resistance, so the spinning will become lower, and it would just because.
I agree with that.
Okay. Oh, you mentioned over there that if you drop the dice at too large a height, it will be too random, right?
Yes.
What do you mean by too random?
Like two random is like it would just rebound to like that much height, so you would have to be that certain lower height that you could observe this phenomenon.
Then did you not consider the depletion of energy when the dice hits the floor then?
Yeah, I consider it, but it would just because the height would just become lower, so we only observe the lower height ground. So the higher here we assume it as a chaotic system.
But if dropping it from a larger height makes it more chaotic, wouldn't that be better for your experiment? Wait, not your experiment. Wouldn't it be better for this experiment? Dropping from a greater height to make it more random? Would you agree?
I agree, but we can quantify.
So you did no real experiments, right?
What was that?
You did no real experiments, right? But you did not.
Yes, I did not.
Okay.
They changed up the operating time. Okay, review it as well.
I'm reviewing the number 7 3-side dice. So here's the problem statement. Our main focus should be that how should cylindrical dice be rolled to ensure randomness? What relevant parameters affect the landing of cylindrical die? And how can we use these parameters to find the physical and geometric characteristics of a 3-side die? So for the reporter's performance, we found that he has no phenomenal investigations. His theory involved band area and approximated ranges of values. And his experiment, there was no personal experiments, only a simulation based on the using the report. The pros of his report were that he included 10,000 trials, which is a lot of trials. And he also included an online program. He considered, but did not quantify the coefficient of restitution. And the material of coin does not influence his results, so he is correct in that. And he attempts a theory. The cons are that there is no demonstration. There are no personal experiments, only the simulation. His theory is incorrect, and he only gives a range and without an actual number for the ratio. There is no head or edge fall probability. He did not mention chaos. He did not mention conditions for randomness. And engines cannot simulate chaotic systems because that is the nature of chaotic system. And probabilities should be inputted first. So that means that his data, if he uses his probability in his data, that means his data was fabricated, and he had bad time management. For the opponent's performance, for the summary, he mentioned the geometrical characteristics. He mentioned the geometrical characteristics and dynamic motion and quantified probability. And the pros were that he identified a lack of experiments. He mentioned drop heights, which indicates the importance of potential energy, and he identified the importance of cross-solid angle and coefficient of restitution. For the cons, he does not talk about the velocity simulation. He incorrectly thought that spinning the dice causes a difference because the chaotic system makes it so that spinning the dice will not cause a difference, and he is inefficient and not precise. So the first discussion topic was counting. Did you count the dice in the simulation? And the report said that no, the program counts. The reverse does not see the relevance of this question when the number of trials is already measured. The second topic, did you change dropping height? Did you get a boundary height? The report said yes. We agree with the opponent. We believe that increasing the height also increases the randomness. However, the opponent says that there's an upper boundary to this height. We believe there should not be an upper boundary to this height because dropping it from greater height also increases randomness, which is good for the experiment. For the third topic, the opponent asked if the material was wood and if it was rigid or not. The reporter said that you can change the bouncing in the situation in the simulation, which does not answer the question. And we believe that as long as the die does not deform, the material should. Okay. For the fourth discussion topic, the drop height, what makes it land on the head or tail? Angle and torque affected by geometry. The reporter said that I agree with that. So we believe that this point is irrelevant since if initial energy is enough, the system will already be chaotic and the torque is therefore negligible. For the coefficient of restitution, the reporter said that they believe it is important and we agree with both. The opponent also found that there was no error analysis for the experiments and the reporter also agreed that there was no error analysis. And we believe that because there was a lot of data, error analysis was not necessary. For the question discussed, they both, do you think the system is chaotic? They both said yes. They both said yes because spinning is relevant, and we disagree because because the system is chaotic, spinning would not matter. And of course, we said that these guys identified the system is chaotic, and to the questions, they have that.
Okay, before the conclusion remark.
First, I want to reply to that reviewer said about that the simulation cannot include the chaotic system. For my limited knowledge about the chaotic system, I believe that the chaotic system is caused by a series of variables that cannot be detected or, yes. So those are all considered in that programming simulation, which includes both air resistance and bounces of the dice that I believe it is quite complete. And also, yes, there is still a lot of considerations that was not included in the simulation or the experiment I made. Yes, so I will both that the height and yes, the both that the reviewer and the opponent's variables that they mentioned should be considered in my simulation, so it can be more accurate. I believe that is all. Thank you.
A question for you.
Okay, during the discussion, reviewer mentioned about the material. They are not the same, but if the shape is the same, then the probability is the same. So I want reporter and opponent to comment about this statement. So do you agree or partial agree, and which part you don't agree? Okay, so the reviewer said that, we talked about how about different materials of the die, right? And the reviewer said that although the materials are not different, then if the shape is the same, then the probability is the same.
To clarify, I said that the material does not matter if it is rigid. If the body is
Okay. So, could you say that again?
The material does not matter only if the material is rigid.
Okay, so I rephrase my question. So, how about elastic material and the rigid material? What would be different to change the result? So,
Are you asking me?
yeah, three of you.
Okay, it will not change the result because of all materials, it is still a chaotic system. In chaotic system, how high the material passes does not matter unless it does not bounce at all. Because you can drop from very high, even if it bounces very little, you can drop from very high and the system will still be chaotic and still produce a random result.
So the opponent think that when doing an experiment from a certain height, we do need to consider the coefficient of restitution, and I think that it would affect the possibility.
Agrees with both of them. First, if we drop the dice from a high enough places, that the material will not matter anymore. Most of the variables should be considered anymore because it is, like you mentioned, it's a chaotic system, that there's too much series of variables that cannot be detected or considered. So the material or how did you flip the coin or not, those variables will not need to be considered in the, if you drop the coin high enough.
Okay, you use the term chaotic or chaos. So when you say chaos, do you mean it like randomness?
No, I have a definition of chaos. My definition of chaos is that small changes in the initial conditions cause drastic changes in the result. Which is
So it's different from randomness.
it's the same as randomness. Because
The same.
Because you cannot control.
The same or different?
The same.
The same. Okay. What about you?
I've done some experiment with the chaos.
No. Just answer me. When you talk about chaos, is it the same as randomness or not?
Okay, yes.
Yes, the same.
Same.
Okay. You.
I want to clarify that I actually have a really limited knowledge about the chaotic system. And, for me, it's
So
like
you don't know.
it's like quite different from the randomness. In my opinion, it's quite a little bit.
Thank you. Because there's still some time, I would like to ask the reporter, how long does it take for you to carry out 1,000 times throwing the dice?
It's simulation, so it's
Yeah.
like super quick.
So why did you just do two aspect ratios?
Oh, I did for. What can you repeat your question?
Why you just do two different aspect ratios, like the ratio between the side length and the radius of the side?
That variable was not considered when I did the experiment.
show the reporter.
Just a minute.
Okay. Okay, for the reporter, please show the score. 5, 5, 5, 3, 5. Okay, for the opponent. 8, 6, 8, 5, 8. Okay, for the reviewer. 8, 6, 8, 6, 8. Okay, so we end this section.
Thank you.